Okay, let's continue on our topic of elimination reactions of alkyl halides. And the first reaction, we've already talked a little bit about review what alkene structures look like, carbon-carbon double bonds, and the stability of alkenes. And so now let's take a look at our first elimination reaction, which would be a way to synthesize an alkene, which would be a way to create an alkene from an alkyl halide. Okay, and the first mechanism we're going to see is called the E2 mechanism. The E2 mechanism is called that because it is an elimination and it is bimolecular. It is bimolecular. That's what the 2 stands for. What does that mean? That means there are 2 things coming together in a one-step mechanism. So it is a one-step mechanism, very much like the SN2 reaction. And so what's that 2 that in the SN2 is the same 2 that we have in the E2, a one-step mechanism that is bimolecular. It needs a strong base. So what do we recognize as a strong base? If you had to guess, if you had to name a strong base, you might name something like hydroxide. That would be a good guess, and that would be correct. Hydroxide is great at doing the E2. In fact, any CO minus compound like, sorry, any anion like hydroxide, so RO minus. So in other words, methoxide, ethoxide, propoxide, anything that looks like hydroxide is also going to be a very strong base. And we might even see a nitrogen anion base. So if we had NH2 minus, that would also be an extremely strong base. That's probably not one we're as familiar with, but if you think that oxygen is a strong base, then nitrogen would be an even stronger base because nitrogen is less electronegative and doesn't handle the negative charge as well, right? So this is even less stable than hydroxide. Thinking about the REO factors that might stabilize the negative charge, because this is less electronegative. Nitrogen is less electronegative. This is even more reactive, and that makes it a stronger base. A stronger base. So these are all very strong. Okay, and the rate is going to be what we have in common for our bimolecular reactions is our base is going to be reacting with our alkyl halide in that single step, and so that's what makes it a bimolecular reaction. The rate is dependent both on the concentration of the alkyl halide and the concentration of base that's used. Okay, so what does it mean to be a base? What does it mean to be a base? A base is something that attacks a proton. Attacks a proton. Remember, acids donate protons, bases accept protons. So bases deprotonate other compounds. So let's take a look at an example here. If we used NaOH and we react it with this alkyl halide, what's going to happen is, let's draw in one of the hydrogen atoms in this compound. What's going to happen is the hydroxide is going to attack that proton, So if we use our curved arrows, it's going to attack the proton. And normally when we do a proton transfer, a deprotonation, we would just put the electrons right here, right? That's usually what our deprotonation mechanism look like, but we're not just deprotonating, because what we have right next door is we have a leaving group. Remember, that's what's special about alkyl halides, bromide, chloride, iodide, is they all serve as potential leaving groups. So that's how we saw substitution reactions being possible. And now we're seeing that that's what makes elimination reactions possible as well. Okay, so what happens is these 2 electrons actually come over here and form a pi bond. So we're going to turn this single bond into a double bond. And as we do that, that would make this carbon have 5 bonds. That's not possible. So what happens at the same time in this concerted mechanism, we kick off the leaving group. So 3 curved arrows are required for the E2 elimination. And what does our product look like? We're now going to have a double bond between these middle 2 carbons. So we make what kind of product? We make an alkene. We make an alkene product. So you could describe the E2 as a way to synthesize an alkene from an alkyl halide. Okay, what other byproducts did we make here besides just the alkene, just the organic product? We kicked off our leaving group, so bromide is generated. Our leaving group has left, and if we used hydroxide as our base, what do we form when it deprotonates something else and it accepts that proton? We form water. So those are our byproducts that we can show in addition to the alkene. All right. So why is it called an elimination reaction? Because we are eliminating a hydrogen and a leaving group. So the loss of HBr overall, right? We're losing this hydrogen, we're losing this leaving group. The loss of HBr is called dehydrohalogenation. Sometimes you'll hear the E2 mechanism described as dehydrohalogenation. Okay, now I've described the hydrogen as the beta hydrogen. What does beta mean? Well, alpha is the position where the leaving group is attached. And so the next atom over, the next position over is described as the beta position. And so it's one of those protons that gets removed. So we're always going to have our leaving group, and on the adjacent carbon is where we're going to lose that proton. And that's how, when we take a group off of each of those carbons, that's how we now are able to make a double bond between those two carbons. All right, so it's our one-step mechanism, bimolecular elimination E2. Okay, let's think about what are some things that we could study about the E2. One thing is going to be the stereochemistry of the relationship between the beta hydrogen and the leaving group. The other question is the regiochemistry. If you have more than one beta hydrogen to select from, if there's more than one alkene that's possible, how do we know which one is going to be formed? Okay, so let's look at both of those features. First of all, the stereochemistry of the E2. Now take a look at the way that I drew this example. Do you see that I had the hydrogen pointing straight up here and the bromine pointing straight down here? That is actually the required stereochemistry of those two groups. They need to be anti to each other, one straight up and one straight down. So when they're 180 degrees from each other, we describe that as anti-coplanar. Sometimes it's impossible to get exactly anti, so a more precise description is to call them anti-periplanar, because that's what we would call us if it was almost 180 or close to 180. I usually just call them anti-coplanar because that's an easier way to describe it, easier term to remember. And so what we could do is we could describe the E2 elimination as anti-elimination. So how do we implement this when we're looking at a reaction? Okay, if we take a look at the substrate that we're doing right now, if we wanted to do an E2 on this alkyl halide, if we take a look at our leaving group, here's our leaving group, and do you see a beta hydrogen? So on an adjacent position, this carbon does not have any hydrogens, but this carbon does. It has only one. So these are the two groups that we're going to be eliminating. We want to lose HBr. And right now, those two groups are not anti to each other. H and Br are not anti. Remember, if we viewed it from this perspective, from the side, and we looked at that Newman projection, that's when we usually use the terms anti. So if one was straight up and the other was straight down, that they would be 180. But they're not. They're both in the back of the ring. They're actually gauche to each other when you look at if you were to draw the Newman projection. But that's okay, because this is a single bond, so we could just rotate around that bond to get them anti to each other. And so so if I draw the backbone here like this and put the bromine here and the hydrogen here, now they are anti. They now have the necessary conformation. Okay, so the question is, what happened to the other four groups that were attached to these two carbons? And let's make sure we put them in the correct position. So if I'm taking this hydrogen and moving it to be in the plane, that means I'm taking that hydrogen and I'm tilting it forward into the plane, right? If you kind of think about standing here and grabbing onto this like it's a steering wheel, you would have to turn that steering wheel clockwise to move that hydrogen up. So what happens to that ethyl group? When you turn that steering wheel clockwise, this hydrogen comes forward into the plane, this ethyl group gets pushed back. It gets pushed back. So this is going to be my ethyl group. And what happens to the methyl group as I turn this steering wheel to the right? This methyl group was up here and now it just comes down here. It's still a wedge. It's still a wedge, but it's going to be down in this direction. Okay, so work on it a little bit. Make sure you can kind of picture taking all three of those groups and you're rotating them all in one direction or the other. Okay, so if I'm still kind of standing over here and looking at that perspective. Now for this second carbon, I'm going to bring the bromine forward. I'm going to bring the bromine forward as well. So it's like I'm taking that steering wheel and now I have to turn it counterclockwise to bring that bromine forward. If I bring that bromine forward, what happens to that phenyl group? It gets pushed back. It gets pushed back. So that phenyl group, remember this can be abbreviated as pH for phenyl. And so that will now be in the back position. And the hydrogen that's on that position again stays as a wedge, but now it's pointing up here. So work with models a little bit, get some practice with this, convince yourself that that these two structures are equivalent. I've just twisted around that bond looking at different conformations of this compound. So now that they are in the correct conformation, now I'm ready to do the E2 elimination. So we're going to react it with some strong base. And we're going to look at the E2. So what happens here is our base comes in, whatever our strong base is, and it can do the E2 elimination, attack the proton, form the pi bond, kick off the leaving group. Always those same three steps. Those same three arrows for the single step, the concerted E2 elimination. Okay, and so we're going to get a double bond. Now, where is that double bond? Where are these groups going to be? They're going to be frozen in space when we go to draw the alkenes. So notice that this methyl group and this hydrogen, CH3 and H, were both wedges. They're going to end up on the same side of the alkene. And we could see that here. They're on the same side of the alkene. And so this is going to be the only stereochemistry that's observed. We describe this elimination as being stereospecific. Stereospecific because we get exactly one specific stereochemical outcome. And in other words, I don't get the one where, so you can see that my phenyl and my methyl are trans to each other. I don't get the one where the phenyl and the methyl are on the same side. That is not formed. That would not come from the anti-elimination. Okay, one other way to view this elimination is to look at the Newman projection, because that's again where we usually use that term. So again, here's my point of view looking at the Newman projection. Remember, this represents the front carbon and this big circle represents the back carbon. So when I see that now, there's my hydrogen and my bromine that are anti to each other, That's usually when we use the word anti, was to say that they're on opposite sides across from each other. That dihedral angle is 180 or close to 180. We could also call it anti-periplanar instead of anti-coplanar. Okay. Let's see. So once again, the hydrogen, we could look at it from this point of view is again, so the hydrogen and the methyl were on the same side. They're going to be frozen in space because this is, as we bring down the pi bond, we flatten out, it was tetrahedral. Both those carbons are going to be planar now, and so they get trapped in whatever relative position they were in the starting material in the transition state. That's where they end up being fixed in the product. Okay, so let's take a look at another example. Again, if you want to try this on your own, you can pause and work on it, but we'll go through it together. So is my first of all, identify my leaving group. That's always step one, is find your leaving group. That's pretty easy to pick out because it's going to be a bromine, chlorine, iodine. It's going to be one of the halogens. And what else do you lose besides your leaving group? You lose a neighboring hydrogen. So is it this hydrogen? It is not that hydrogen. That is on the same carbon. It's on the neighboring carbon. There's my beta proton. So remember, we're going to be losing HBr overall, a hydrogen from one carbon and a bromine from an adjacent carbon. That's our E2. Okay, so right now, once again, they are not anti to each other. They're both in dashed positions. So what we have to do is we have to rotate about that bond to get them anti. So the simplest rotation in this case would, since the bromine is kind of pointing up towards, the top of the page and the hydrogen's down towards the bottom of the page, the least amount of rotation to get them anti to each other would be to have the bromine up and the hydrogen down. So both of them in the plane, a one straight up and one straight down, is always going to correlate to this anti relationship, one straight up and one straight down. Okay, so now there's going to be a dash and a wedge here and a dash and a wedge here. We have to figure out what happens to the other groups. What do you think about that phenyl on this first carbon with the bromine? What happens to that phenyl if you bring the bromine forward? If you bring the bromine forward, think about turning all three of those groups at the same time. Bringing the bromine forward pushes the phenyl group back, So it's going to be on the dashed position. I think the easiest one to locate is the one that is initially in the plane. You want to see, does it get pushed forward? Does it get pushed back? Depends on where it's going to go each time. Okay, and how about the second one? The hydrogen is coming forward. So what does that do to the phenyl group? That gets pushed back as well. So both my phenols are going to be pushed back, and my methyl group is going to be still as a wedge. All right, so now I can do my E2. The E2 mechanism is so quick and easy to draw. It's always a good idea to show the mechanism that will help you draw the product, right? 3 curved arrows. Base attacks the beta hydrogen. I use these 2 electrons to form a pi bond. And then that pi bond formation, that pi bond is what's going to kick that bromine out, kick that leaving group out. So there I do my E2. And so what does the product look like? We could just draw our alkene. Our alkene is going to be planar. Our alkene is going to, make sure you have kind of 120-degree bond angles as best you can. And if anything doesn't look quite right, you can adjust it a little better. All right, so now it looks like a nice 120 degrees. Okay, and so where are we going to put our groups? So once again, the 2 groups that are dashes are going to be on the same side, and the 2 group that are wedges are going to be on the same side. So let's draw the hydrogen and the methyl on one side and the 2 phenyl groups on the other side, and that is going to be our only product. So we describe it as a stereospecific reaction that is the result of anti-elimination.